Thanks for having me. I have to confess, I've not been paying a lot of attention to Bex recently, so I'm excited to hear more. But I did put together these slides recently for a summer school that Matthias had at the Institute about gravitational waves, and they wanted me to talk about the electromagnetic signatures of binary black holes. So I thought maybe that material would be of interest to you folks as well. And it gave me the opportunity to review the state of that field. And I would say that while we maybe haven't progressed dramatically in terms of finding concrete evidence of subparsec binaries, there has been quite a lot of effort in the community to systematize what we're doing, and there are some beautiful new reviews. And so I'm happy to talk about some of that today. So obviously it's a golden time to study supermassive black holes. None of you need me to tell you that. We've got Nobel Prizes for the dynamical mass of the black hole at our own galactic center. We have the Event Horizon Telescope, which brings you all together. And we have the detection of gravitational waves from the merging of stellar mass, intermediate mass, and tantalizingly very, very supermassive black holes from pulsar timing arrays. And I think this new world of detecting the gravitational wave background from pulsar timing does provide a sort of infrastructure for us to think about all the things we don't know about supermassive black hole demographics when we can really focus on the most massive ones, which contribute to the gravitational wave background. And so roughly speaking, in order to square the background that we measure with what we know electromagnetically, we sort of want to count how many very massive black holes there are. That seems like that should be the easy part, but I see Changpei is in your schedule for tomorrow, so I think she'll probably give you a very clear explanation for why we still have many challenges there. We do want to understand when the black hole mass is built up over cosmic time, and I'll come back to challenges there at the very end of my talk. And then we would like to be able to understand the timing and number densities of supermassive black hole mergers, and that's where the gravitational waves can be very powerful, but we also would love to complement with electromagnetic constraints. And so in the context of this talk, I had started with scaling relations, but since you have Changpei, I don't think you need me. I'll just very briefly flash through some of the challenges that we continue to have here, despite more than 2 decades of making very robust dynamical black hole mass measurements. And this is, of course, for sources within 100, 200 megaparsecs, when we can resolve the region of the galaxy where the black hole dominates the gravity. We can use tracers, gas, or stars to give us a dynamical enclosed mass for the black holes. What we would like is that all of the different techniques, whether it be a gas disks or stellar kinematics, would give us the same answer on average. We could understand the uncertainties in each, but it turns out to be very challenging to get complementary methods for the same object, so that understanding our systematic uncertainties continues to be a challenge, and that's a place that I think Bex could make contribution. Therefore, we don't yet know the scatter and the scaling relations, and there's still some concern in the community that maybe the sample of galaxies for which we have dynamical black hole masses is biased compared to the full galaxy sample. And then finally, Changpei and her collaborators have been really pushing on this issue that if you want to use black hole scaling relations to get at the black hole mass density locally, you really have to understand the properties of the galaxies as well, which turns out to still be a potential systematic. So I think that's a whole interesting set of challenges to talk about that Bex could contribute to. But I really wanted to focus on this issue of electromagnetic signatures of subparsec binaries. And so it turns out that while we know that galaxies merge And we know that the supermassive black holes will become bound in less than a Hubble time. Every sort of stage of hardening comes with substantial uncertainties, including the dynamical friction on large time scales, what dominates the spiraling in once they're within 100 parsecs, and then of course this well-known final parsec problem, where I think there's quite a bit of consensus in the community now, and the fact that we detect the gravitational waves, we know that black holes don't stall at a parsec forever, but I think we still don't actually know what drives the hardening within a parsec. How important is gas? How important is our stars? And then that, of course, determines how much gravitational radiation we get from a given black hole binary. And so it would be nice to have some electromagnetic
What?
examples.
Oh, you may want to wear long pants. Yeah.
I think someone just needs to mute. I'm going to keep going. So this is a beautiful figure from Dan D'Orazio and Maria Carisi, who wrote a nice review recently. And this basically shows the different electromagnetic signatures that people have been talking about for many years as a function both of the orbital period, or the separation of the binary, and the mass. And so some of these things I won't touch. I won't touch LISA or the idea of helical jets as signatures of binarity, but I did want to talk about some of these signatures that could be on larger scales than the VLBI a little bit here. So the place that I did a little bit of work, this idea is, so if you have an accreting black hole, around that is not just an accretion disk, but also a broadline region on sort of light day scales. And you could imagine that over some range of separations, you could actually see shifts in the broadline region as the two black holes orbit. And this should get us to within sub-parsec scales in principle. And so when the Sloan Digital Sky Survey started producing many AGN spectra, people immediately started picking out extreme broadline regions with multiple velocity components. Many of these turned out to be strange geometries rather than binaries, but the hope remains that if you monitor AGN over time, you might be able to see these spectral shifts. Again, the orbital periods here are still pretty long, hundreds of years to see full orbits. But nevertheless, if you have large samples, you might hope for some constraints. And Mike Heraclius and Jesse Runno have been monitoring now for more than 15 years a sample of objects that they selected to have high velocity offset broadline regions. And they do have a few candidates that are showing Keplerian-like velocity shifts over time. And so if there were a sample to watch, that would be the one. They've been working very hard at this over many years. And you know that Sloan 5 is now starting to gather time-resolved spectroscopy for many AGN, which in principle should allow us to do this kind of experiment at scale. The problem is that intrinsically broadline regions flicker in velocity, and we can watch individual systems do this with Sloan 5 data. And this serves as a very substantial source of noise if we want to use these spectral signatures to identify binaries. And so that will be a hard noise limit that someone smart needs to figure out how to overcome. Okay. The other sort of promising technique that people have been excited about for a while is, and now getting us down to, year-long orbital periods, so really close binaries now, is the idea that you could have the secondary basically gravitationally kick the disk of the primary with periodically. And so you could imagine that on top of the normal AGN variability, there could be a quasi-periodic signal from the binary. And so people have been publishing papers pulling out apparently quasi-periodic variability from AGN since Graham 2015. So they've done this with all of the photometric surveys, including Gaia and ZTF and CRTS and so on. And the problem is that all AGN vary with this red noise spectrum. And so you get a whole lot of false positives that appear quasi-periodic. And then when you get more and more data, you can see that you've been fooled. And in fact, I think Karim El-Badri has a paper from last week doing this with the Gaia sample, just again showing that most of the time, once you do longer monitoring, you find that the sources are not quasi-periodic. And also, Alberto Sassana and others have shown that if you take at face value that all of these periodic sources are, in fact, binaries with the orbital periods suggested by their periodicity, then you basically overpredict the gravitational wave background. And so there is still hope that with LSST and very long timescale monitoring, we may pull out evidence of very close binaries with this periodic method. But it is hard, and we'll have to understand more about the intrinsic variability properties of AGN to do this properly. And so then, of course, the reason you are all gathered here is that VLBI astrometry is getting more and more powerful. And so there's this hope that you could just directly image some binary black holes. This has really only been done once, and it's not a subparsec binary, it's 7-parsec separation. But it should be in play. Maybe BECS won't be quite sensitive enough to get large samples, but as you start to do space VLBI, certainly the precision should be sufficient to start to actually see both black holes. I wanted to also highlight this beautiful paper that Joan Roble and Lazio wrote in 2022, thinking about the NGVLA, which could also do very high precision relative astrometry at 80 gigahertz. And they were imagining that for a pretty wide range of mass ratios and orbital periods between 4 and 40 years, that if you could monitor over 10 years, and this is in Virgo, so relatively close by, that you might be able to rule in or out a binary. So it seems that I've gone way faster than I expected. The last piece that I wanted to talk about briefly is that, of course, in order to predict the gravitational wave background, we also need to know when black hole mass is built up over time. And yeah, just coming back to Gabby Sato-Polito's paper, you basically can use AGN luminosity functions in some way to constrain when the black hole mass was built up, and the Solton argument suggests that most of the most massive black holes built their mass at redshift 2. But there's a lot of degeneracies in these arguments, and JWST has really been shaking up our view of when the first black holes grew and when that black hole mass was assembled. And so I didn't think I had enough time to really talk about this, but it seems like I have plenty of time. So I have been heavily involved in searches for redshift 5 and above accreting black holes with the James Webb Space Telescope. An interesting thing happens at redshift above 5, which is that for almost all of cosmic time, if you use X-rays and UV tracers to find accreting black holes, you find that something like 10% of galaxies have very active growing black holes. This is true at redshift 2, it's true at redshift 0. But around redshift 5, both the X-ray sources and the UV selected sources drop like a rock. And so the implied AGN fractions also drop. And so if you build models of black hole growth, you have to actually suppress the AGN activity at early times if you think that we're finding all of the accreting black holes with UV and X-ray methods. And this has been a problem actually for more than a decade. And then JWST started observing about 3 years ago, and immediately we started finding whole new populations of AGN using broad emission lines in the rest frame optical, which had been out of reach before. And they seem to be, if we could measure their black hole masses, which is an ongoing source of pain for all of us, it seems that the black hole masses are quite high compared to the galaxy masses. And if you take some of these observations at face value, it seems like we may be way overproducing the black hole mass density at early times. So I could give an entire talk on this, and I'd be happy to talk more about it since I have extra time. But for now, I'll just end my talk by saying there's some really big questions left to understand the black hole population. We still don't have a strong handle on the black hole mass density locally, even though we know there are scaling relations between black holes and galaxies. We still don't know how black hole seeds formed, or really when most of the black hole mass was assembled in the universe. And we're still waiting for reliable electromagnetic signatures of parsec scale black holes. So I finished 5 minutes early, so we have extra time to chat, and I will stop there.
Thanks so much, Jenny.
Trying to stop my sharing.
Okay, questions? Marshall, go for it.
Good morning. Thank you for a really excellent talk. That was very good. My biggest question here is, I believe that the pulsar timing arrays are showing that there have to be supermassive black holes of the sort of masses we would like, in the 9, 10, and the 10th total masses that are close to merger at any one time in the universe. How do we find these in the optical? And by close to merger, I mean well within a parsec. How do we find these?
Right.
They've got to exist, but I don't know of any good candidates even.
Yeah. Well, so Michael mentioned OJ287. People like to put that one forward. I think
That's 14 years. That's not close
not
to
close
merger.
enough. Yeah. I mean, I guess I would say there's no guarantee that such close binaries are actively accreting, or do so in a way that's readily apparent to us as an AGN in the same way. So certainly there's, I think, interesting theoretical work to be done about what the accretion flow, how the accretion flow behaves, and whether some of the very naive assumptions that we make for some of those binary signatures I talked about really even hold. Because for sure we're failing to find them. And, people have been trying very seriously, I think, for a decade now. That's what I was sort of trying to summarize there.
I guess I have sort of a related question, which is that given the extremely high rate of false positives in this field already, and it's so challenging, what do you really see as the smoking gun detection? What should we be thinking of for BECS? Would it, in terms of observing one, right? Is it all about you have to get to multiple orbits, and so 2 years just isn't enough, and we need to be thinking about follow-up campaigns with NGVLA, or is gravitational wave detection single source? Is that going to be necessary to really have confidence? I'm just trying to think, how do we fold this into the BECS observing program as efficiently as possible?
Well, I was actually really wondering about this combination of NGVLA and BECS. That seems potentially powerful, right? If you could, because you will need to see,
Yeah.
if you want to see two, you're gonna have to see them multiple times. And as you say, 2 years is probably not enough. But I assume it has to, we're imagining sources within a pretty small radius. And so it's possible that those two together could really get it done. And I
Yeah.
would certainly love to see a direct detection of a binary. I guess I still worry about sensitivity. Seems like most of these black holes are really close to dormant. And so that, I think, makes it hard. You showed a beautiful map of all of the sources you think you can detect. And that's
Right.
probably not enough to find one. So I think that's my other concern, right? I don't know the way around that.
Yeah, I think that's exactly right. That if the reason we haven't seen them is the lack of sensitivity, BEX is not the answer to that. Like we fill in a
Right.
missing piece of parameter space, which is angular resolution, but it's unclear whether that's really the missing piece of the puzzle here. Leonid, go for it.
Thank you. Thank you very much, Jenny, for a very interesting review. I was reluctant to make this comment here because that might shift us quite a bit to a distance from BEX. But once the word smoking gun was pronounced, well, I can't help. The point is that in VLBI domain, not only potential future direct astrometry of the moving binary systems can be approached, but even now, a smoking gun of jets demonstrating some periodic fluctuations might help. Actually, well, to answer, for example, question raised by Marshall, where are those supermassive black hole binaries? There are examples, there are sources which show astrometric oscillations. These are on milliarc second scale, and that's certainly not closed motion of black holes themselves, but this is exactly smoking gun. And that might help to answer let's call it Urban's paradox, like Fermi paradox. So where are they? If they must be, we don't see for some reason. So the short final statement, VLBI still can help to find some candidates through the smoking gun from their orbital motion. Thank you.
Yeah. I mean, I've always thought that these jet signatures seem really squishy in similar ways that the variability does, which is, it seems like there are other ways to make jets wobble besides a close binary. But given the state of play, I think we got to try everything, right?
Yeah. Alex, go for it.
Jenny, what's your guess as to the likelihood that OJ287 is a binary? And if so, what could the role of imaging be there? Because that's on the BEX target list, and that's our leading candidate for what we think might be a binary, but I'm curious what your perspective on that is.
I'm not the right person. It never felt totally certain to me, but I also haven't, I guess it continues to show this periodic behavior over many years, so it's got to be much better than all the other things I showed today. And it's relatively nearby, right? So maybe there's a multi-messenger approach.
So worth checking out, but not a slam dunk.
That's what it feels like to me. But I don't have any slam dunks, so.
I'll take it.
Okay, I just have one more question for you as
Yeah.
sort of a practitioner in this field. I just remember 10 years ago, there were all these possible detections, right? You showed the plot from that Graham paper, and it seemed like this looks pretty solid. A few more years, and it's going to be absolutely certain. It's like a 2 sigma, it'll be 5 sigma before we know it. What happened to all those, and is there still a lot of optimism in the optical searches? Is it just we need more numbers and it's and they'll hold up, or
with the quasi-periodic variability specifically, I think there's a large amount of convergence that most very large fraction of those are false positives.
But so given the high fraction of false positives, do you think that we would ever be certain of identifying one as a binary, or is it always going to be
I mean,
an asterisk?
I guess I maybe feel a little bit of hope both for the spectroscopic techniques, which are on much larger scales, and the temporal variability, that we will have large enough samples that we can characterize the non-periodic parts of the AGN light curves well enough to try and tease out on top or below that a periodic component.
Yeah.
But Kareem's abstract ends with, even the ones that are close binaries must be dominated by a non-periodic component, because once we went and monitored these Gaia things over longer timescales, we don't see the continuation of the thing that looked periodic to begin with, right? And so I think that means that we're going to have to be smarter at how we model the light curves, because all AGN vary and we're being swamped by the non-periodic part, potentially even if there's some quasi-periodic part under there. And maybe that means more chromatic information, but maybe it also means leveraging the full ensemble better, understanding the variability properties better, which I think is in play. I mean, I have the student Amy Secunda with Yanfei Zhang, and she's doing these shearing box simulations of variability and the lags across bands. So it's possible that we'll be able to clean up the light curves better with time.
Got it. Okay, last question to Marshall.
So I would think that even if you had a situation where you had a close binary and it cleared out all the gas and dust around it, which I think, is not a bad assumption, you would still have stars coming in from outside from time to time and getting, eaten and absorbed, and that would create a lot of signal in the optical. That would create, X-rays and other stuff. Is it possible that that's what we're seeing with these quasi-periodic things, that they're quasi-periodic?
Tidal disruption events? I think you could ask Anna Ho about TDEs more specifically. There's certainly been a suggestion that you get a higher rate of TDEs when you have binaries, because the dynamics in the nucleus certainly changes, but mostly no. These are mostly just persistent AGN that we've seen over more than 20 years. And when you take a small slice of their light curve, it can look like it's variable, periodically variable. And then when you look at it for 5 more years, you no longer see that period. And this is just because it's the noise spectrum occasionally causes false positives, and we pick out those false positives as if they were binaries. But when we follow them up over longer timescales, we see that it is not quasi-periodic variability.
Thank you. And of course, that's very common with any fractal or chaotic type.
Correct. Yes. It's not a shocking result, but it is somewhat painful because, you make these beautiful sinusoidal periodic variability curves and then it all goes away.